Hello and welcome back to our discussion of window functions in SQL. We will spend this entire video on the discussion of one particular use case. It's this use case that talks about the visibility of spots in a hilly landscape. Okay, this will lead us to a discussion of a particular window function or a particular group of window functions, the so-called scans. Okay, so scans are really widely used in algorithmics and in different specifications of computations and computer science. They're really pervasive and they have a wide variety of uses, and we will see one of them in the upcoming minutes, and then in later videos we'll point to other uses of so-called scans, and window functions can express such scans. Okay, we will also see a use of the partition by modifier that we've just introduced into the syntax of window functions. Okay, but let's first have a closer look at what's happening in this visibility example. So consider this person standing somewhere in a hilly landscape. So you see the rolling hills here of this landscape. And we are asking ourselves, which of these spots, for example, spot P1, P2, P3, which of these spots can we see if we are this person at this particular point P0 here? Okay, so you probably would expect that you can see P1. I will try to draw a straight line here. Because there is nothing obstructing, nothing blocking our view, probably we can see P1. It's probably different for P2. There's this hill blocking our view. There's no straight line view, no straight line that is unblocked from ourselves at P0 towards P2. And of course, it's completely impossible to see P3 from P0 because P3 lies behind this peak of 800 meters actually. Okay, right. So the distance in this hilly landscape is measured from point P0 on. So we would be at position 0 meters here, and the x coordinate would ascend to the right here. So that peak is actually found at a 100 meter difference, 100 meter distance from our position P0. Okay, so which of these points are actually visible? Can we compute that? And there is a very nice and very elegant method to do just that, and we can transfer that to SQL. And this visibility method is depending on view angles. When I'm talking about view angles, I'm talking about, let's first look at this left-hand side of the picture here. Okay, all right, so I'm standing at position P0, and I'm asking myself, hey, can I actually see this point, this edge of the hill? I probably can see it, but we will determine this visibility in terms of the view angle alpha. The view angle alpha between this horizontal line and this point of interest. Okay, so this view angle alpha is just the arcus tangens, as you can see, of the height difference and also the distance of this particular point from my own position P0. So just using this application of the arcus tangens on this ratio here, on this height to difference ratio, will give us the viewing angle alpha. All right, so this is the viewing angle. Okay, so determining visibility based on these viewing angles is actually really simple. We would just start here at our own position P0 and then move or march from left to right here. So we would move in the direction of increasing distance, of increasing delta x values, if you will. So we are ourselves at delta x 0, and as I told you, the peak is already at delta x 100. And we would move the computation from left to right. Okay, At each point x here, we would just measure the viewing angle from P0 to the actual point at this current position x. So it will probably be 0 degrees at this particular point. It will be 0 degrees at this particular point, but it will be somewhat more, namely alpha 1 at this particular point already. Okay, and if we delete this, well, we would continue to compute viewing angles. For example, for the point P1, it would have a viewing angle of alpha 2. It would have a viewing angle of beta here at this particular point. P2 would have a viewing angle of gamma, and P3 would have a viewing angle of delta. Okay, and the rule for visibility is very simple. A point is visible if the viewing angle it's been associated with, beta for example, is at least as large as the largest angle that we have seen so far on our walk from left to right. Okay, so on our walk from left to right, we would just record the maximum viewing angle that we have recorded. It would start out with 0 in the beginning, but as soon as we have reached this point, this would be the maximum viewing angle that we have seen so far, and would just record this alpha 1 here. If we progress to the right, then alpha 2 is a steeper angle than alpha 1, and we would just record alpha 2 here. Okay, when we reach beta, we would just ask ourselves, is the viewing angle of beta larger or at least equal to the maximum viewing angle we have seen so far? That's alpha 2. If beta is indeed larger than alpha 2, at least as large as alpha 2, then point P1 would be visible. All right. The viewing angle gamma of P2, if you draw the line here, is smaller than the maximum viewing angle. What's the maximum viewing angle at this particular point? Alpha 2. Alpha 2 is the maximum viewing angle that we have seen so far. Gamma is smaller. P2 would be invisible. Okay. Proceeding with our scan from left to right, we would record the maximum viewing angle seen so far. It will probably be alpha 3 from this point on. And since this is the peak in the whole hilly landscape, alpha 3 will be the maximum viewing angle that we record for the rest of our traversal from left to right. And of course, delta will not exceed alpha 3, and so P3 will be invisible. Okay, so the core of the computation is actually this traversal of from left to right and the recording of the maximum viewing angle seen so far. And this is what's called a maximum scan. We would record the viewing angles and only remember and would only record the maximum viewing angle seen so far. At this point, for example, it would be time to replace the maximum viewing angle seen so far. It would now be alpha 3 and not alpha 2 anymore. And it will stay alpha 3 for the rest of the traversal. This is a maximum scan. All right. And such a maximum scan is actually very easily expressed using window functions. We have already mentioned that a particular form of windows, those starting at the very beginning of an order table and those reaching up to the current row, starting at the beginning of an order table and reaching up to a current row, that those would be equivalent to scans. And indeed, this would be such an instance of a scan-like operation. And we will see that we can easily express it via SQL and window functions. So what would be the input data here? Let me take a sip of coffee, I'm sorry. What would be the input data? Of course, somebody would have to tell us the position P0 of our viewer of the whole scene. So we would just be told that our viewer P0 in this examples and in the tiny sketches you have seen on the previous slides would be at x equals 0. But P0, our viewer, could be located anywhere inside the landscape. And currently we are assuming that the viewer is looking to the right, so to larger x values and towards larger x values. We would also have a tabular representation of the hilly landscape. So at one particular coordinate x, the height, the altitude of the hill at this particular point would be this many meters. So the altitude at x 120 would be 500 meters. All right. What we then want to see as an output is a visibility information. So if we ourselves are at this X position, then the visibility from this viewpoint in the hilly landscape would be this table of Boolean values. So from the viewpoint of X equals 0, we could see the spot at X equals 10, but we would not be able to see the spot at X equals 120 in our example. That would lie beyond the 800 meters peak, and that would mean that the point is invisible. So we want such a Boolean table or a Boolean column as visibility information once the computation is done. All right. And this would be the core of the computation already. This would be the core computation. It fits onto one slide, which is so common for declarative programming languages and also for the highly declarative SQL language. So let's see what we are doing here. You see that the whole thing is proceeding in two phases. All right, we would first, in the first phase, we would compute the viewing angles. The viewing angles with respect to our own position P0. Okay, so we would just traverse the map and consider all the points that lie to the right of us, because we are assuming that the viewer is facing to the right. Okay. For each of such point in the map, we would just record its x coordinate and then compute the viewing angle. The viewing angle is just, as I told you, the ratio between the height differences and the distance from ourselves, from P0 to the currently considered point at n.x. This is all we need to do. This is just computing the ratio, computing the atan, and then converting that to actually degree values. This is an optional step, but let's think in terms of degrees here. Okay, so that would be the viewing angles at position x. This is all we need to compute the max scan. Okay, so we would iterate over these viewing angles. And then sort them, order them, according to the distance from our position P0, so that we really traverse the viewing angles from left to right. So we traverse the viewing angles with increasing distance from our viewer. And this order by clause will just ensure that. So P0.x minus AX. AX is the current angle position that we are considering. This is the distance of the viewer to the current position that we are looking at. Okay, and we order the rows inside the angles table by exactly this measure. So we will start with the minimal distance from the viewer and we'll end up with the maximum distance from the viewer. We are really performing a march, a scan from the viewer into the landscape, away from the viewer in a sense. This is the order by that we are using. And you see that nothing else is inside this frame specification. Nothing else is in the frame specification. And if you remember the syntactic sugar that comes with SQL, this means that the frame that we are specifying here, it starts at the very beginning of this table. So it really starts at the beginning of the viewer and extends until the current row. It extends until the current row that we are, the current position in the map that we are currently looking at. And over this frame, from the very beginning, starting at the viewer to the current row, we will compute the maximum angle. And this is just a maximum scan. We will record the maximum angle seen so far from the viewer until this very point in the map. Okay, the maximum angle seen so far is just recorded with the current x position that we are looking at. And that's all we need for the maximum scan here. This will leave us with a two column table, the current x position and the maximum angle from the viewpoint of the viewer that has been seen so far. Everything else is a simple comparison of viewing angle that we've seen with the maximum angle at the same x position. This is really trivial. Everything else is trivial, and that's the whole core of the computation. So let's switch over whether we can really play with this in the SQL terminal. All right, so this is the map, a preparation of the map table. Empty map table done. All right, let's situate ourselves as a viewer at X position 0. And as you can see, we could easily modify this here. But this 0 position coincides with the sketches you've seen on the slides. Now a representation of the hilly landscape. And you see that the granularity of X values have recorded the altitude of the landscape in distances of every 10 meters here. So any finer granularity, more coarse granularity, everything would be fine here. This is just for illustration purposes. So let's define the hilly landscape. We could now check that this definition of the hilly landscape, for example, we have the 100 meter distance, we have the 800 meter peak, that this specification of the landscape is indeed the landscapes that has been sketched on the slides that you have seen. But, and we could probably very easily generate an output, a rendering, maybe a text-based or ASCII-based rendering of the hilly landscape, so that it would look like on the slides that you've seen. But let's make this into a quiz. So I would ask you to maybe think about a query, a SQL query, that would turn this map table into a representation, into a text-based rendering of the map that looks like this. I'm sorry for switching slides here. That looks like this. So no need to include the axis here, no need to include the spots. You don't know whether spots are only given the map table, but maybe try to render this text-based representation of the map. All you need to know to do that is already present in your toolbox. All right, so let's switch over here. Okay. So yeah, then let's start. It's just an elaboration. Just a few more details have been added to the core SQL computation that we've already seen on the slides. So, for example, this tiny P0 table, it's a single row table with only 2 columns. This would be used in the query to encode our X position and our own altitude. All right, so we would just look up in the map at position P0, at X position P0, what's the current altitude here? So that we would, we need the current altitude of the viewer to incorporate that into the altitude differences when we compute the viewing angles. Okay, so let's, it's already over here, so let's check the contents of the P0 table, which only encodes the viewer position. All right, so let's see. Okay, so an X position 0 at altitude 200, that's the viewer position. Okay, we've got that already. Okay, so then let's check the map. Let's check the map to the right of the viewer position. Okay, so all the X positions to the right of the viewer positions are considered now, and we will compute the viewing angle. Okay, and you can see where the altitude of the viewer is referenced in the viewing angle computation. This is just the A10 over the ratio of height, difference, and the distance, as I've shown you already, and that would give us the viewing angles table. Now, let's see how that looks like. So from the viewpoint of the viewer at X equals 0, this would be the viewing angles. Okay. So the viewing angle would be 0 in our direct vicinity, but they would be much steeper when we walk further into the landscape. Viewing angles are increasing and then decreasing again, even to 0. This is an indicator that there is a hill somewhere really close to us. And then viewing angles would get really steep, up to 80 degrees here, to the maximum of 80 degrees, 80.5 degrees, when we reach the peak of the 800-meter mountain or largest hill in the whole landscape. And of course, beyond that peak, the viewing angles would decrease again. These are the viewing angles computed using a simple A10 application. All right. Now to the core of the whole thing, the max scan. Okay, so given these viewing angles in this order, in increasing X order, in increasing distance from the viewpoint, compute the maximum angle seen so far. So at this point, the maximum angle seen so far would be 0. At this point, it's still 0. At this point, it would be 71. At this point, it would be 78. At this point, it would still be 78 because we are recording the maximum angle seen so far. The window for this current row would extend up all to the beginning of the table. Recording the maximum angle in this window would still record the 78 degrees angle here. And we would proceed that way until the very end of the table. So we would expect the maximum scan of these angles to be a strictly increasing sequence of viewing angles. All right, so let's see whether this is indeed what we get here. Yes, it looks like it starting with 0 and then 71 and then 78. It stays that way until we reach the peak. Until from then on, the maximum viewing angle is 80.5 degrees. Okay, so we are almost at the end already. All that's left to do is to compute the visibility, and the visibility is just computed from the viewing angles at particular position X, comparing that viewing angle with the maximum scan, with the maximum viewing angle seen so far. Of course, in both tables we would refer to the same X position. Well, and if the viewing angle is at least as large as the maximum angle seen so far, that point at position X would be visible, otherwise it would be invisible. That's all we need here. Activate the entire computation. All right, and that's it. This is the visibility information. We could see stuff that is in our immediate vicinity. Then there's the first hill, and we could see things on the ledge of the hill, but anything beyond that hill will be invisible to us. But then when we approach that really high peak inside the hilly landscape, things that are facing towards us will then be seen, but anything beyond the peak will of course be invisible to us. This looks like reasonable visibility information in the hills, computed using the maximum scan. This would be the core of the entire thing. Perfect. Let's add a tiny twist to the whole thing. And let me scroll through the slides. Yes, that would be the twist. Okay. Let's add the twist that our position P0 is now really somewhere inside the hilly landscape. You see that I've relocated my little figure here to this X position, and it's now standing on this mountain peak here. That's P0. In our computation so far, we were looking to the right. What's the visibility on the right of our position? I would like to have a computation that evaluates the visibility to the right this way and to the left. And I would like to specify a single query for that. Okay, so we would just proceed as before, but we would need to make sure that we are aware of the fact that we are either right or to the left of our viewer. Okay, we would still perform scans. We would still perform max scans. Scans that go along the direction of increasing distance from our viewer. All right, so in this to the right, this would be the increasing distance from our viewer. To the left, this would be the increasing distance from our viewer. It would go this way. It would extend to the left here. Okay, and you can see that I've recorded the delta x values below here. Of course, delta x equals 0 would be just where the viewer stands, and then the delta x values would increase to the left and to the right. All right. This calls for a use of partition by that we could add to our frame specification. Of course, we are talking about two different partitions here: the partition to the right and the partition to the left of our viewer. Okay. So here, the part to the left of our viewer is identified by this relationship, that the difference between our x position and the x position that we are looking at is larger than 0. Okay, right. So I think we are standing at position 90 here. 90 minus whatever the x position somewhere here is 50. 90 minus 50 is 40. That's larger than 0. So that would characterize the left partition. The right partition is, of course, characterized by the fact that this difference would be less than 0. Okay. And this is a criterion, a partitioning criterion that we could use to really partition the information to the right and to the left of our viewer and find the appropriate visibility information here. So the core of the computation, the max scan computation, would now look like this. Okay, so much of the rest of the query will stay the same. We will see it in the editor in a minute, but this would be the max scan computation. Okay. Again, we would of course consider the distance from the viewer to the current point that we are looking at. We would consider this the ordering criterion. This term is the delta x, the distance from our viewer, and we want to order rows in increasing distance from our viewer. But we would need to do so. We would need to do so in the two partitions to the left and to the right of the viewer separately. And this would be the partitioning criterion. We would look at the sign of the difference between this P0 and the current position A dot x. We would just look at the sign. Sign is a built-in function in PostgreSQL, and I've already indicated the possible values that this sign computation might take on. If this difference is indeed less than 0, then the sign would be -1. If this difference is larger than 0, then the sign would be 1. All right. So that would be the partitioning criterion. That would be the two partitions that we make up. There would be no 0 partition here, because we would of course exclude our own position P0x from the entire computation here. Okay, so we would end up with the -1 and the 1 partition. Okay, and in these partitions we would consider rows in increasing distance from the viewer. Okay, so let's see how this looks in practice. Okay. So this is the same hilly landscape that I've defined in the previous example, but I will relocate our viewer to position P0.x 90. Okay, done that. This is just the old hills that we know already. Okay, same quiz applies, of course. Alright, so again, we would locate ourselves in the landscape and check the altitude that we are standing at. We are standing way higher now at x equals 90. Okay, then we would again compute the viewing angles. Nothing has changed so far. While this predicate has changed, we are now considering any particular value on the map, regardless of whether it's left or right from us. We are excluding the value that is at P0 itself, and you see that it's a good idea. Otherwise we would divide by 0 at this particular spot. Okay, so then the partition by and the order by in the frame specification that we are using for our max scan, and this is just the SQL code for the slide that you have seen before. All right, so ordering criterion, distance from ourselves, partitioning criterion, are we left or right of our current position. This will lead to 2 partitions. Everything else stays the same, and this has not changed at all. All right, and this would be it. This would be the visibility information that can look to the left and to the right, and maybe it's worth to take this visibility information seen in this output table and just annotate it in the visibility in the map of the landscape, of the hilly landscape that you've seen on the slides, just to assure yourselves that this visibility information makes sense. That these are the points, the truths are those points that can indeed be seen from our viewpoint. The points beyond the peak, for example, are still invisible from us. But there is quite the valley that we can spot from the, oh, it extends even further. There's quite a range of points here, a whole valley of points that we can easily spot from our elevated position next to the peak. All right, so that would be scan operations and also an application of partition by in window functions. I hope you found that example interesting already. Many more of this kind, even cooler, will come up during the lecture, and I'm looking forward to discuss these with you. Take care and see you then. Bye.